Well, it lagged when you redeemed the thing. Hello there. Oh, I can't hear anything. No, for some reason I've been lagging a lot lately. I wonder why. I feel like there's a process in the background that's loading my CPU. System D? What? Chromium, Steam Helper, Turing Complete. I mean, doesn't seem to be anything that bad. For 14 hours? I mean, I think he should get more viewers. Can I? Yes. You can tell that everything lags. So maybe I should close one instance of Chromium, you know? That might be useful. Starting game development 17 hours ago. 14 hours. Two views. I mean, that's about the numbers I've been getting. Back like a few. Back like year and a half ago. When I was just starting streaming. I mean, I've been getting the same numbers for a long time, for a while, and I think it's still the same. Also today, like I was preparing for stream and the birds scared me so much. I dropped my water. What kept me motivated to continue streaming when? Like also camera is like off sync. Here it is fine. Yeah, now it's fine. So I mean, I don't know. I was just like, I'm programming anyway, so why not just stream this? Why not let people see it? And when I then there was Nigel. Oh wait, it is you. Then there was Ian. Ian was Ian has been on a lot of streams. You can tell by stream elements. Ah, camera sync again. Like how I have just 4 of 30 FPS variants. Okay, that was better. So yeah, now, I mean, I don't know. But I don't know what kept me motivated, to be honest. Anyway, look at this. Look at this. I have 7 hours of play time on this game. And it's time we start a new computer. The thing unlocks a component, the thing doesn't. Let's do this one. Let's do XOR. I wonder what XOR does. Using the instructions of your computer, reads the input twice and XOR two values together. Oh my god. It's still an outventure. I mean, it's easy, right? We just input it, copy. Into register 0. I don't need to do this. Copy into register 1. Then how do we XOR stuff? Do I have an XOR? I don't think I have an XOR. But XOR is 3 elements. There's a main page. Choose tables, no, universal gates. No. Of course, he was just going to mention on the Discord server before I give my stream notification. From NAND to Tetris, I have seen a series of YouTube videos about from transistors to Tetris. I haven't really finished watching that though, but I didn't see that. I did not know that, to be honest. I mean, you can... Well, basically that's what we're doing here. And we are gonna... I think we have a Tetris level here. So yeah. But, I mean... Ben Ether did do a breadboard computer, and I think that's the most famous computer out of logic gates series. I mean, yeah. So I'm...
In each project, you have to build a set of chips. And for each such chip...
Hold on. So I assume... does this do any sort of hardware? What is this? Is there any sort of hardware interaction going on? Operating system, compiler, huh? Virtual machine. Okay, well that's a bit a lot further than Turing Complete goes. That's an interesting thing. So yeah, anyway. To check out the Morgan's law. So it doesn't say anything about XOR. I don't remember how to do XOR. Let me think. It is easy, right? It's or and not and, right? It's or and not and. Or is it's compute or yeah, it's just the two values. I'll just or them. Okay, let's do 2 and 3. No, let's do 1 and 2. Then I'm gonna copy register 1 or that. Then so I need to end it with a not end. Do I even have a bitwise not? I don't think I have a bitwise not. So I'm gonna copy this into register 3. I'm gonna copy register 1 and then I need to node this, which means I need to do an end, right? So I copy into register 1 and end that, and then I need to end the result with register 3. Register 3 into register 1 and copy into out, right? Choose the bits of inputs 164 and 73. Choose 7 not 0, huh? Well, let's debug it. Stop and step. Okay, so we input the values. I wish I could see them in binary. Hold on, let me restart it. 73, 164. for... Oh no, I need to copy register 2. So we OR them, copy it into register 3. Then I take register 2 again. And we add them. Copy it into register 1, we enhance them, we end it with that and output. Okay, let's mix some registers. I don't know why Jesus. By the way, I could have just modified the hardware, but it's not worth it. So now we can go to byte XOR, which unlocks a new component, huh? And byte constant. Is this a hardware level? And the byte constant is also unlocks a new component, which I think... You know what? I've been doing byte constants before, I think. But let's do XOR first. Hold on, a circular XOR, what? Create a a circuit that XORs to byte bitwise, pairwise XOR together each bit. Well, I did not think we'll have to wait that long. And by the way, if I open Steam again, I wanna check out the achievements, because I think it's there is an achievement for this one. So we've got condition 10. No, I mean there might be, but probably not. Probably like hidden. Maybe if it might be hidden. Okay, so I can either split and do XORs, or I can do logic. So I do 2 ends. I do a NOT. And I do an OR. Hold on, why am I doing an AND and then a NOT if I could just do an AND? It doesn't make any sense. Okay, let's AND those together and OR those together as well. Then... Oh wait, no, I need an AND here. So it's and then this. Oh my god, this circuit is gonna be tiny. Unlocks 8-bit XOR and 8-bit XNOR. Well, I don't know about XNOR, but yeah. So byte constant, that would be useful. Create a circuit that always outputs the number 164. And you don't give me anything. Sure. 164 you say. I've been doing stuff like that for a while, and I thought I would go to instruction, but okay, fine, we're gonna do it manually. 164. Done. Unlocks an 8-bit constant. Well, that's useful. Now, what is this? Equality. Oh my god. When both inputs are the same. I mean, I guess I can subtract. Or I could subtract, or I could do it differently. Let me think. Which one is best? Or actually XOR. I could XOR them, you know? Even XNOR them. But, like, then I need to end all of them. Or I could sub and check for 0. Either way, it's probably best to split them. Or is it? No, I'm gonna do XOR and then split them. Logic, where's XOR? Ah, they didn't give me the XOR. Hey, why? Okay, then I could beat them. We could add a negation. I mean, that's simple, right? We're not even... We're not checking for the fastest implementation or something. We don't care about carry, so this should be 0, right? Is there a fast way to check if it's 0? I mean, I can just do it later and then make sure all of those are zeros. Wait, can I move the... Yes, I can move out. So I could do a big OR. It's like OR those 3, OR those 3. And then do this, and then also 2-bit OR. I guess that's a possible way of doing it. I mean, we're not looking for the best solution, right? We're not forced. Okay, so those are not equal. Wait, I need an N. Wait, I need an odd. Hold on. I need a not in the end. Or I could do a 3-bit NOR, but that's not a thing, so I'm gonna just do that. Unlocks an equality component. I don't know if I need that, to be honest. But sure. So this is unlocks a component signed less and unsigned less. Why are we making comparison circuits? I don't think we need comparison circuits. Input is less than the second. Interpret the byte as being unsigned. Okay, we're just gonna subtract it again. So I'm just gonna subtract one input from another, and so if unsigned less than, so if the first is less than second, what is it gonna be? So I subtract second. So carry should be 0, right? So we do not carry. Oops. So we do not carry, and just hope it works. Is 155 less than 0? Wait, right. I need to flip a different one. To flip this one instead. Hold on, this still doesn't work. This is signed. Hold on, this doesn't work for signed stuff. Okay, how can we do this? I mean, I guess I could try this regular query. And so if this is gonna be bigger, then it's gonna be... Is 0 less than 255? This is 1, this is 0. Okay, I guess I need to do something differently. I'm actually not sure how to do this anymore. So if I subtract... so 0 minus 255, for example. This number is... so this should be true, right? This number is less than 0. Okay, can I connect this? I wonder if I can. I can? Hold on, I could do this all the time? What? So this is false. So I subtract 0. This number is positive. I need to detect if the number is negative. Problem is... problem is that it's signed. I mean, it's unsigned. What? Let's switch to signed less than first. It's one of the first line is less than the second number. Interpret as being signed. Okay, this should be easier. This should just work. Right. So we subtract one from the other. Let me check for carry. I'm not sure. So -1. This should be true, so carry should be inverted. Right. Okay, it doesn't quite work like that. Oh, why is -1 not giving a carry flag? Cause it's being... Hold on, I think I know how to fix that. I just need to check if the number is negative. Like that. Wait, inverse it again. -127, -127, -128. Oh my god. It's problematic. I mean, I could split it into bytes again and check for each bit, I guess. So that I could compare numbers. Or carry. No, maybe I should put an OR here, because we do have the thing. Come on. Won't work. Signed less than. No, that's not true. Hold on. Oh, what does this number actually represent? So if I subtract the second one from the first one, if the second one is bigger, it's gonna be positive, and the output is gonna be positive if the carry is false. So I wonder why it doesn't work in this case. Because -1 is like, I mean, I know why. It's just not signed extending it. I don't know how to fix this. Just split them and work with values. Throw bits. So I have the sign bit first. Save the sign bit. So this number is negative and this number is positive. It's obviously false. Well, I need to flip that. I feel like there's a much better way to do this. I mean, because I can't hardcode everything. Let's try addition again. Means subtraction. Should be easy. Why? Why can't I do this? Why can't I do it? Maybe I should like power on the carry. Like all the time. So if I subtract the second from the first one, if the first one is smaller, then it should be negative. Problem is I can't negate -128. Wait, what? Yes, I can't negate -128. It's overflowing. Why? Maybe I should be twice noted instead. It's not helpful. Wait, that's negation. I need to be twice noted. Logic not. Because I am adding a carry. Hold on, how? I have a note. Oh wait, I can't place it, that's why. Here. 76 less than 76, true. And not equals. Maybe I should remove the carry. 76 and 77. I mean, it won't even work with carry. -76 minus 77 should be negative. Why is it possible or positive? And -78 still should be negative. Why is it positive? '76, 178. 178 plus 1. Ah, it's 255. Why? Should I handle the signs separately? I don't want to handle the signs separately. I'm going back to negation. Six minus 78. Minus 77. This should give me negative number. The addition is not currently there. What does it do? To check the number, not the. It gives me all ones. I mean, I can put an OR, but I feel like it's not gonna save me. Yeah, here. 127 minus 128. The negation doesn't work, of course. I mean, I could do a note instead and push the carry. Feel like it's not gonna help though. Still true. It's not gonna help me. I need to extend it to 9 bits. You know. Or I could shift it. So the highest bit is always 1, and here, well, actually it depends on the highest bit. Let's try extending it. So the highest bit, I just duplicate it, and negation will flip it. I'll just do it manually. So negation is just a node, and let me move this. Oops. I think I have an idea. It's just a node and then end one. We're gonna end one later. Oh, why is it all ones and negative 128 is being 0? Oh wait, that's because I flipped it. Of course. So your signed extension should still work, right? So then if I add it together with this one, and yeah, I need to also do another addition, and then I need to carry. I like how I can toggle this, but I never actually really use it, and it's annoying. So I need a half header. I don't have a half header. I mean, I don't need a half header. I need a full header. So here it's always I need another splitter. Okay, let me get rid of that. Let me add another byte splitter. So I flipped this one, I didn't flip this one though. Then I'm gonna do addition. So the signed I need to signed extend it, which means I copy this bit for the last bit, and I copy this bit for the last bit, and the result should be the sign, right? 76 less than 76. Okay, it's again, it's equality again. I want to see the value here. It's 0. It's 0, 0, and so it's negative 0. Wait, what? Wait, no, it's negative 256. Ha. What? I mean, it's carrying. Actually, I don't want to check carry. I want to check the beat. Right? Wrong. No. Doesn't work. Wait, the first beat, because it's hold on, I am splitting nothing. It's a byte. It's not a byte. Okay, this works finally. This is so annoying. This was so annoying. But now I think I know how to do this one as well. So I do the same thing. Basically, so I invert. Where is the node? So subtract the second one from the first one. In order to subtract it, I also need to power this. So 55 unsigned less than 0. It's if I subtract 0 is 255, obviously. 0 subtract 255 is what is it? 1, which is well 1. Hold on, this is wrong. Where is it? What do I do negative 255? 1 of few zeros and another 1. I mean, let's try. Wait, it's wrong. Let's try doing the same thing. Maybe it's gonna help. Maybe it's gonna work. So I'm inputting carry, but here I need to do an unsigned extension. You know what? Yes. So this one is always on. So I'm basically adding an always 1. So I basically need to invert this, right? Wrong. Probably wrong. Oh, it works. Wow. Okay, so it did work. It's just extension. Okay, so hold on. Widen oh my god, oh no, oh my god, that's gonna be something. Let's just read the level. Create a device that saves the program output on even ticks and outputs both bytes on odd ticks. That is insane. Do I add a counter as well? I think I need a counter as well. Yes, I do need a counter. So I put a counter here. So we're doing wide instructions. I mean, sure, that's right. That's good. Yes. So I need a register. Is there a register plus? No, there is no register plus. So lower byte instruction. Save. So I save this value. So save bit. I need to split the counter. Hold on, how is it? What's the schematic named? Ah, default. I thought it's a new. I thought it could be a new CPU that we're making, but not yet. So on even ticks, I save it. So this is gonna be mediated. So I save it, and also I always load it. Output both bytes on odd ticks. So just this, you know, or it's not gonna output 0 on even ticks. Okay, that's fine. So then I'm gonna do an 8-bit switch. Do I have an 8-bit switch? I do have an 8-bit switch. I need a few of those. I need 2 specifically. So I do this one. And then I also need this one. Oh wait, it's a signal. It's a way. Right, it works. Unlocks a program, programmable memory component. Wait, what? How can it unlock a program? Or is it a program that has two outputs? White spaghetti. Finally, it's time for you to start building the leg architecture. Yeah, I wanted to check out leg again. Leg. In the last stream we found out about this page, which is a subset of ARMv8A, and it's available on GitHub, so it can easily be there. This is insane. Say simulator, browser-based simulator, subset architecture like v8. I hope it is, or something as cool as it is. We're on live still. Yes, I am. So let's try. Let's not try. Let's do this. The leg architecture is a computer that takes 4 bytes per tick from the program. First byte describes the operation, called the OP code. Since many operations take 2 arguments, like add or etc., the second and third byte are for the arguments. Since most operations return one result, the first byte is for the result. OP code, argument 1, argument 2, return address, memory addresses, registers, counter, input, output, result, arithmetic. Well, that's basically the schematic of a computer. The following are setup steps that needs to be done in order to complete the level. Click the schematic icon and create a new empty architecture. Place a program block with 4 outputs. Place a counter, set its increment to 4 and connect it to the program block. Add 6 registers or custom components with registers. I mean, I had argument before, you know. Anyway, add 6 registers or custom components with registers. Finally, in this level, OP code is always 0. That means we add argument 1 and argument 2 and save the result to the destination. Of an argument to the destination first one of these places. Okay. Implement the more OP codes, which will require a different ALU than in the overture, than that of the overture. Okay, let's see. Register 0, 1, 2, 3, 4, 5. Counter. Program counter and input output. Wait, I'm in the overture schematic. They are telling me to create a new one. Oh my god. We're doing this. Use 4 bytes out, custom. Shift right, wait, no, IO. Program, programmable memory, RAM. There's a RAM component. And the level stuff, which, yeah, we don't talk about that yet. So this is input and output, right? Can I move those? I can move those. This is the computer. Okay, so program loads 4 bytes, right? There's a counter. Can I set an increment on counter? Set the counter to increment to 4. How? Do I have to do it manually? Oh, there is a setting. That's insane. I mean, it's easy to, well, do this manually. I just bit shifted, and that's it. And it's not even components. Any components, it's just wires. Let's switch 6 registers to the map. Custom. There was a register plus. Yeah, register plus. 2, 3, 4, 5, 6. In component 0. Register inside. Okay, let's do a custom component, I think. So I wanna do a new component. Oh my god. So we're doing architectures. So we have separate components and architectures. That's interesting. So let's create a new component, which is gonna be our memory. Oh, I mean, I'm still not sure about this one. Actually, no. Let's not do that. Go to the factory. Switch to some, for example, this and remove this, because I do need input output and similar. So let's go back. So we have a program. We need to somehow place registers. So it doesn't really matter for now. Well, let's put registers near a counter, I think. Thinking how to position it all. Also, we've got a lot of space, right? I mean, that's an architecture. That's cool. I wish I could order like manufacturing of this thing on an actual chip. So register count, register 6, 7, and 8 is gonna be this one. Okay, so I take 6 registers. Let me put program away for now. And there's an input as well, and output. Should I flip them? Like vertically? Maybe, no. So like I have the register here. Okay. So I have program memory. I know how to structure it. I'll link them. So 0, this is 1, this is 2. I mean, thankfully I don't need to worry about wiring those ones. 5 is gonna be this one. Wait. This one. 6 is gonna be wait, I can do 6. I can do an output. Okay, let's do this. Wait. Next component 5. 2 points to a counter. Wait, I need 5 to point here. 6 to point here. And 7 to point at the output. Set the registers and implement the add optic code. I mean, so I need to somehow select the register. Let me reread the code. The numbers, the things. So 0, 1, 2, 3, 4, 5. 6 is counter, 7 is input output. Okay. Should I do a bus again? I guess I should do a bus again. And I think I'm gonna restructure this again. So let me put. So I have program here. That now. Let's do a bus. Like it's so empty that I don't know where to put stuff. I wish they locked it again. Okay, so let me move this here. Oh, so it's so hard. Let's do a bit. Let's do a decoder. One bit decoder. It's need a 3-bit decoder. Okay, so let's do a pass, I guess. Let me just move this out of the way. And I'll have a switch on the program counters. Let's leave it for later. So we do a decoder. That's just gonna take. Which one is the? So this is the load bit. This is the input 1. And then I'm gonna do a switch here. It's gonna take the output of a counter. So all of this. Wait, it's not gonna work like that, is it? Yeah, it's not gonna work like that because I can't have a single bus. Do a regular register instead. I mean, I can. I need all of them to always output. How do we do this? Let me. Let me do a different register. Register always. So the always active register. This is just a register that's always active. And we don't have that. We just. So there's no load, there's just a store. Memory probe. Yeah, so there's memory probe. No, that's about it. Okay. It's a bit it's a bit this, but okay, sure. Let me switch back to the leg and see, replace all of those by the always registers. 3, 4, 5, 6. So I have 6 registers. Now I need to I need to output. So I need to be able to select two of them at the same time. So we have two buses basically. Let's also do a multiplexer. Let's do new component. Big mux. Or actually like 3-bit multiplexer. Okay, so we have an 8-bit input. Actually like 2, 3, 4, 5, 6, 7, 8. So we have 8 inputs. This is how can I rename it? Also this one is gonna be up. And I'm gonna move it like that. So this is text. This is a select. Yes, let's do select. Now this is one. It's gonna be input 2. Or actually no, this is 0. It's gonna be input 1. It's gonna be input 2. It's gonna be input 3. It's gonna be input 4. It's gonna be input 5. This is gonna be input 6. And this is gonna be input 7. And also I should have probably used like those custom inputs. Wait, there are no inputs with yes, there are no switch inputs. Okay, that's fine. That's good then. Because we have a switch. So just do 8 switches. 1, 2, 3, 4, 5, 6, 7, 8. Just 8 switches and a 3-bit decoder. And the byte splitter because I decided to put a byte here. Or should I have used just 3-bit inputs instead? I mean, no, I think so I do an byte input. Then I decode it. Okay, so hey, select here. That's better. Wait, is it? Oh, are those boxes the ones that I think those boxes are the ones. And I can't put an input perfectly symmetrical here, sadly. You know what, I'm gonna do corners instead. Shift here, here. It's not in the corner. Oops. Here. Then I do this here, here, and this is the last input. So I select. I mean, I guess I can put select inside of here. Then, and so I have one output. which is always active because it's a multiplexer. So it's gonna be like here. No. So we have 8 somewhere here. Let's put it. So I have a decoder. Okay, I'm gonna rotate it. I don't care what they say. Also, what's the disable? Okay, I'm not gonna disable it. Okay, I can do this. Okay, it's still using this one. Oh wait, that's because switches. If I put them in, it's not gonna be using this one. Yeah. My goal is to make it as compact as possible. And maybe I shouldn't have done it like this way. So I do the first input to the first switch. Maybe I should like move this up a little so it's more compact. So the first input to this switch, second input will be to this switch, third input, fourth, etc. Yes, this is a bit messy, but it's fine. Also, do I need to do memory probes for each of them? I mean, I do need to do memory probes for each of them, but how? How do you put them in? That's insane. Now, I need to do memory probes. Oh wait, no, I don't need memory probes here. I wish it was like more, more field. I guess I should have like moved switches in a different way, and I'm gonna do that, I guess. So it's gonna be one switch per input instead of this mess. Wait, I'm using wrong keys. It's gonna be much less of a mess. Right. I mean, it was kind of beautiful, I guess. So this one is a bit complicated. Other ones should be simpler. Okay, it is gonna be a bit of a mess. This is gonna be a bit hard to route because of the decoder's position and of how routing works here. So maybe I should move output like here. Looks better. I don't care. I mean, it looks bad, honestly. But I guess it's okay. Maybe I should, you know, maybe I should move select like up here instead. And then I can move this into the same square. And yes, reroute everything again. But you know, it's fine. So it's reversed. Ideally, I'd reverse it somehow. No, okay, I'm doing it in this way. No, it's fine. Let's go back now. Like, I don't like that thing appears all the time. It's a 3-bit multiplexer. Could I rotate the label somehow? I don't know. I don't think I can rotate the label somehow. I guess it's fine then. Also, I think I messed up some... Yeah, I haven't connected some inputs. Because they were square. For whatever reason. Back. Now, I can actually multiplex those register inputs now. Probably not like that one. Cover registers. Also, there's this level screen. Something like that. So I'll have a program counter be here and level inputs as well, which I may want to be always active. You know, what if it checks for the activation? I probably want to be active whenever it's actually selected. Then it's annoying. So I'm gonna keep it always active then. This register. Okay, we're not looking at that again. Set it up to do the add OP codes. Okay, this is the multiplexer number 1. Then let's add the multiplexer number 2. Okay, now this mess of a thing either well, I don't even know. Here. Oh, that's better. Is it? It's a mess. It's a total mess. Okay, should definitely do those two wires in a different color. Let's do. So let's select this color for inputs, instruction inputs. Then we'll have an 8-bit splitter here for the demultiplexer. Yes, this one is save. We're gonna have a single output bus, right? No SIMD today. What if we wanna store and jump at the same time? Okay, so let's do a simple addition. This, and then so yeah, this is the output. This is messy. Also, I need the counters value here. No, I'm gonna do gray again. This should work, right? Yes, it works. It is wire spaghetti. It is a real wire spaghetti. Implement the following opicals. You're kidding me. You're just throwing this on me. Also, this unlocks something unknown. Oh, the opical not ignores the second argument. Add sub and or not XOR. Those are bitwise. Do I just select the input? They have enable components. That could be useful. Okay, so this is a mess. This is a real mess. I don't want to stay with this. I do like multiplexers, I don't like the mess. I think we should spread it out. I shouldn't have done this. Let me just move this somewhere. Somewhere. So I have program. Maybe I should put the program under the screen. Whoa. And bring back the input and output here. It doesn't really matter where input and output are, so I guess I can put them there. Okay, so the program here, under the screen, where it was supposed to be. Then we have we'll have on this everything else on the side. Cut all of this. So we have this. This is the output thingy. I'm gonna put it here. Also, color coding is important, so I'm gonna do output as. Which color should be an output and which color should be an input? I think lime could be the output. and then in input could be like this magenta color. It's like red and green, but well, yeah, different. Comments. I can comment wires. Test. How do you remove the comment? Yeah, that's better. Now, wait. I just pressed escape in order to get rid of this thing. Okay, so the input. I think I'm just gonna cut all of this. Move this somewhere. So how the registers? Let's spread them up a little bit. This is always like third argument decoder. It's like how it is. I'm just gonna put it here. That's better. Now I'm gonna spread registers out a bit. Okay, now those are the registers. Main thing. We have a program counter here, and then an input and output of the level. This is an input which is, I mean, I kind of want to keep the input always active. Also, I'm gonna rotate components. So input this color. Now, also this should probably be like here, and maybe nah, yeah. Now I'm gonna do lime. This lime, this kind of color, for the saves. So we're gonna have an output bus. Also, output bus should probably be like in a different place. Yes, I'm gonna do a second lime color for the actual output bus. Or you know what? Maybe it should be like here. And select this again. Let it go around. So I do this color for the bus. It should actually move this. And do the same thing here. Wait, different color. This one. Color coding is important. Right. Now I just connect all of those registers to the output bus, and yes, we need to do some fixing here. Ah, it disappeared. No. Redo connections. Like how it goes around. sometimes, most of the time I don't like it. Okay. Now we've got our multiplexers on the other argument. So do magenta for the selection. I'm gonna do this. First input. I'm probably gonna do it like that. The second input. Something like that. I don't know. No, I don't like it. I don't like how the wires are routed. I mean, I should probably just do this instead. No, don't wanna do that. Come on. It's not that hard. Well, this does not feel good. Oh my god, what's wrong with it? Okay, anyway. So the wires. Just wire it all. Oh, wait, it's not right. This goes here. And this one goes here. And also here. Okay. Here. Now. This thing doesn't really look much better. Okay, so OP code instructions. Now, we actually need some instructions here. I guess let's go with an ALU. Let me new folder overture. What's old components? One. Old delay line, old full adder. Wait, what? Root wire bit. What is this? There's no. Can I just remove this folder? I'm gonna remove it. I'm gonna delete it. I'm not sure if I did it right, but it's okay. So ALU of the overture, I'm gonna also do leg, and that's where we're gonna add. That's where we're gonna add the ALU for the leg, which is what we're gonna be editing right now. So conditional module goes into overture as well. Deck. What is deck? Let me see what deck is. Oh, a decoder. Wait, what? It's also overture. Multiplexer. Register always. Register plus goes in overture. Shift right. That's legacy technology. Now, multiplexer and register always are pretty generic. So we could go. Okay, so LU. IO input, 8-bit input. It's gonna be the instruction, which I think I'm gonna do is this. Or OP code. And then we're gonna have 2 inputs. Here, and we're gonna have an output, a single one to get output. I think I'm gonna do like this and like this. And the corners here. Something like that. And now we need to. This is input 1. For input, let's do input A. Let's do labels. Input B. This is gonna be output here. Now let's do the stuff. I need to check the logs. 0 is add, 1 is sub, 2 is end, 3 is or. So 4 is not, 5 is XOR. How could I compress this? Let me see the manual for the modern flow. So AND is just inverse of an OR. I guess I should just do a big multiplexer. So just do 3-bit mux. And I already forgot the OP codes, but yes. Here it's gonna be just regular colors. 8-bit decoder. Actually, you know what? I have a custom 3-bit multiplexer. I can just use that. So I compute all of them and then I multiplex it. Now, for the computations, we have add and sub. Well, add and sub are gonna be, yeah, add and sub I can just mux them. So I do need an 8-bit splitter. Here, a byte splitter, so that bit is gonna tell me if it's add or sub. Bit math add. A bit negation. Well, that's gonna be hard to fit inside of the space, so I suggest we grow a bit more. One more cell. So for the first two, we have the add. They're both add. They're both gonna be add. Second one is gonna be multiplexed over the first bit. So this is the first input, this is the second input, like that. Now let me check out the opcodes. And or not XOR. And or not in the XOR. We're gonna be redoing it, trust me. And or not and XOR. So let's order them, I guess, in this way, and or not XOR. Okay, yeah, I think I routed it correctly. Now for the inputs, we're gonna have this one, and we're gonna have this one on the different layers, something like that. Wait, no, it does not take it. So for the end, I'm gonna do this, and I'm gonna do this. So this is not. This is an OR. This is gonna be. Okay, this is gonna be dance. You know what? Remove that. Connect this to OR, connect this to XOR, and just connect this like that, up like that. Now this should, I think, work. So just take an ALU, ALU. I don't care that it's broken right now. Don't care about that right now. So the output bus in green. We're gonna be color coding it. Okay, so I'm gonna drag it here so that I can connect stuff to it easily. Then the two inputs are just gonna be connected in there, and the OP code, which I'm gonna take gray, cause yeah, we've talked about that already. I'm just gonna move here, and this looks pretty good. It's gonna work. 16 register. Register 1 should have value 8, not 0. Wait, what? So tick 0, add 8 and 8. So it's 16 and it's register 0, right? Right. Next. Wait, it's register 1, not 0. Not register 0. Wait, what? So have register result address register 0. Yes, 16. Now subtract register 0 from in and then subtract input. Okay, so this is 7, which is, yeah, outputs 8. This one outputs 8 for some reason. And where does it take this 8? It should be outputting 16. For some reason it's outputting 7. For some reason first argument 1, for some reason is 7. Which is not register 0. Hey, you... what? 7 is not register 0. Wait, I forgot to connect the counter, that's why. So this is gonna be a gray line here. Now this should work, right? This does work. Type miscellaneous. Immediate values, oh my god. Immediate values and conditions. Are we just finishing this computer in 2 more lessons? If so, it's gonna be a bit insane. I mean, actually, product of nibbles is far away from this. It's nice to useful to load the value directly from the program instead of from the registers. It's called loading an immediate value. In lag architecture, we signal when we want to do this directly in the OP code. You can do that in the following way. When the 8th bit of the OP code is 1, the use argument 1 as immediate value instead of as a register value. When the 7th bit of the OP code is 1, use argument 2 as an immediate value instead of as a register value. Okay. Well, that complicates stuff a bit. I mean, I need a multiplexer. So I need 2 multiplexers here. So what I'm gonna do is I'm gonna draw this differently. So it goes here and then it goes here, like that. Oops. So we're gonna connect ALU to that, and And also we're gonna take an 8-bit splitter. Put it here. Connect it. So we have those 2 bits, which signal immediate values. Can you tell me again? 8-bit is argument 1. So this is argument 1, that's argument 0, right? So we do multiplexer. Not multiplexer. You know, by default it's gonna be this. Grace control, right? So this is this is gonna be that. Now, this is gonna be this. This is gonna be this. Right. And now those are inputs. Now this would theoretically work. It does. And conditionals. Add if statements to your circuit. For the if statement, hold on, what? You're asking me to add an if statement. Okay, for the if statements, the 2 arguments are compared, and if the condition is true, the counter is set to a jump address. And for the if statements, we do OP code argument 1, argument 2. Reversal codes at 32, 33, 34, 35, 36, 37. Use unsigned less greater than for the comparisons. Each OP code does what the name implies. For example, the phone jumps to byte 16 for register 0 is less than register 1. Well, this is interesting. I mean, 4-byte OP codes and you have just small memory. Just 8 bits address space. So we have a 32. 32 is which bit? Hold on, I can look here. So this is bit. So if this bit is set, we do an operation. We do a different thing. Completely different thing. So and we also select a different output. How do I do this? So I'm gonna do a multiplexer here. Yeah, it doesn't quite fit. It's fine. We can do that. Oh, where's the green? Green's the output. So the output is by default and a constant. Otherwise, if this bit is set, straight line. So I'm gonna want a gray line here. It's gonna go here. This is a jump. And 0, 1, 2, 3, 4, 5, 6. So what's the value 6? Yeah, it should not flip numbers. What, I'm gonna flip it back. Yeah. And route it like that, but I wanna use this color. Okay, now. When there are comparisons, we do different thing. We do a different thing. The condition is also good. Okay, I can't really do it like that. Need to change it. Oh, wait, I can disable the decoder, you know what? I can disable the decoder actually. So this bit, where's the gray? Let's actually do conditional lines in white, because this is like an exception. Okay, so we're gonna disable the decoder also. We've connected that. And then I'm gonna do a separate line that's only enabled on condition. That's gonna set the program counter. Chicken route here, but I prefer to do it here. Now in this space we have an ALU. We need to compare thingy. By the way, I can see instructions are not filled. Okay, I feel like I'm gonna have to fill them. Okay, so we need to do a new comparison, a new comparator thingy. So this is better than x86, I can tell you. Okay. Maybe instead of an ALU, I just put everything here, by the way. I feel like I really want to redo the ALU. If equal, if not equal, if less than or equal. If less than or equal. How it's done is not nice. So we flip the equality bit each one, but it's gonna be okay. I mean, I can use this as a binary thingy. So 32 now. This one flips equality. So 34 and 36. If any of those two bits are set, I flip it again. I mean, actually, who cares? Use unsigned for the comparison. How about signed stuff? Some greater than. Okay, I guess let's do this. Let's create a new one. Not a new folder. So cont for conditional thingy. Have A and B. Here I'm gonna split them apart. So I'm gonna put them in corners again. Input A. Input B. You know what? I should instead copy ALU. Duplicate. So I remove that and I rename this to count. This is just that. So I do another 8-bit multiplexer. I feel like this component is actually useful. However, yeah, it beats mass logic, so we have comparisons. Well, let me check the once again. So less than or equal to, if we flip it we get greater. And it flips again. Oh my god, this is so messed up. So 34 from 36 are different. This is 36, this is 34. So XOR those together and we get this. Let's okay, let's just check for the bit. Let's do compression. Let's do equality first. So do XOR. Where's XOR? XOR. Give me back this. So I do equality. I flip it with the first bit. But so that's the output for first instruction. For first two again. Oh wait, I need a different multiplexer for this. No way, it's not engineered for the thing. I mean, it must be, right? So do equality. When those two are ones, can I see level up? Ah, it's component factor. So when those are ones, I can just decode it and do hard coded them all. I don't want to do that though. So I have a quality. This is the zeros thingy. If those are zeros, or if oh my god, why are the OP codes so bad? In last time we had like everything beautiful, truth tables, etc. Like De Morgan's law can be applied easily using bits, but here they just listed them. If only we could reorder them a little bit. So I have a less than, right? Mass. So unsigned less than. Check if the input is less than the other. And I have a quality. And we do an OR on them. Okay, let's try it. Have equality, we have less than, unsigned. So first of all, well, let's actually do the operations. Good. Now, so let me do an OR on them. An OR here. but so I want to flip the equality sometimes. I want to flip the whole thing sometimes. You know what I can do, an 8-bit decoder. Wait, a 3-bit decoder here. So I decode those 3 bits. Here. And then so I flip it. If so if this one, so 0, wait, no, 1, or so I flip the output. Oh wait, come back. So if 33, or so this one is just flipped this one. 36 and 37. 1 0 0 1 1. So this one is high. So basically all 4 of this, but I only need 2 of those ones. So this flips output, right? Now I just need to select if I do want equality and if I do want the less than, and in which case I want them. And when I need to swap. Okay, so if it's 32 or 33, I don't want the less than. Otherwise I need to just toggle equality. So here if I take all of those 4, so those if this is active, I need this. So I need a switch here. Where's the switch? Okay, now this switch is gonna be active whenever the instruction is right. Then when do I enable equality? Actually, this is pretty good, you know. This works pretty well, I feel like. This idea. Oops. Move this here. Now I wanna toggle equality when. Remember, this one is flipped. So if less than or equal to EQ, not Q. So I need it enabled in the first 2. So 0 1 3 and 4. 0 1 3 and 4. That's what I need. 0 1 3 and 4. Here is when I toggle equality, and yeah, I have mixed this up. Okay, so this one toggles the thing. So I need any of those, basically. I could do a bunch of switches, I guess. Or I can do an OR. don't know about that, to be honest. Also, this is gonna conflict so much as well. So I need an OR on those three. And then I need a 4-bit OR. Which is basically two 3-bit ORs. Yeah, it's two 3-bit ORs, I think. Actually, it's a 3-bit OR and a 2-bit OR. Okay, so this one enables the equality, this one enables the inequality. Let me do this one. It enables the equality. Need a regular OR. Not like that regular OR is that big. This one enables the equality, which I haven't even put a switch on. Which is the something. Now I need another OR, which I could put basically anywhere. But I'd like to put it somewhere here because there are wires, and wiring stuff is hard. Guess I could also move those down. Come on. So I can just do this. Now it's more full. Now I just do a non-equality here. Another 3-bit OR with another regular OR. So it's not gonna be able, you're not gonna be able to tell what's happening. I mean, I can't already. Ah, this broke the connection. Need a regular OR. So I need to OR it with this one. Yeah, messy, but should work, right? Like having, oh my god, having conditionals here is gonna be so annoying. Like editing this is gonna be so annoying. And it's all because of force. It's okay. Let's actually get the conditions thingy. Like conditional. Okay, so I put it somewhere. It's just like an ALU. Now. So one condition is true, and this bit is set. Okay, where's the white? So I need to do a mux. Where's the multiplexer? Here it is. Now I regularly gonna be choosing that, but whenever this one is enabled, I need to choose the input. You know what? I'm gonna do white first. Okay, so this one is the condition. Okay, so I'm gonna connect this to the multiplexer, and then I'm gonna do an AND or a switch actually. I'm gonna do a switch. So I'm gonna do condition. It's gonna be enabling the jump if this one. Short circuit, huh? I've got a short circuit. I haven't never gotten a short circuit in this game before today. And today it's the second one. Outputs 3-bit decoder, 0 switch. I mean, I think I have actually. So 3-bit decoder and a switch. It can't short circuit. When decoder is disabled, why is it like... Why is it short circuiting when decoder is disabled, eh? Now I need to put a switch on here. Like when this is not the case. So this white, when this white is not set. Here. Huh? Ah, that's woke up from nap. Okay. This is messy. Wait. Okay, so I can't even pass the tick 0. That's so bad. If not equal, register 0, register 1. So this is setting it. So condition. Oh wait, I forgot to connect the condition instruction. The conditional OP code. No. It works, but it's so bad. You'll show me some upgrades I can make on the path implementing functions. To implementing function calls. From here on, details are up to me. You won't tell me what OP codes to use and so on. Okay, sure. Tip copy is just add with the second argument being 0. Interesting, yes. Gate score. You can now view the gate score of wires and components. Oh wow. Okay, I can now view gate score. 897. I could do less. Gate 1.1k. Tick 19k. Okay, so I can see gate scores now. It is a bit insane, but I wanna improve it a little bit. What is 8? Is the gate score? Gate score, no, gate score 17. What is the 8? Ticks? Delay score is 4. There's no... What is the 8? I don't get it. Okay, so I don't really like how jumps work here. So instead, I wanna change it a bit. But I mean, right now it's pretty much what it is. So decoder. I do need to disable the decoder. Okay, so let me rewire it just a little bit. So jumps are just special thing. So here we have a line. So this is when jump is enabled. We disable the decoder, we disable this line as well, and then we also enable This is jump mode, and then we also possibly enable this thing. How could I jump properly? So I'm gonna do this now. No. Okay, no. So let me go white again. So I need what? I need the address to jump to, which is on the line. I need the jump enabled and the jump itself. Okay, so let me change this. What is this? Okay, so we have what is this? Jump mode, and this is jump condition. Jump mode, jump condition. Okay, this labeling is helpful. So this is OP code. Out pass output. Now those are the two inputs, which are conditionally immediate. And then we get to this part, which I don't like. Okay, let's do. So let's do white. So we have an ALU. So this, fortunately, in this game we don't care about power consumption, so we have all of those components always enabled and computing. In reality, I think ARM, why ARM was so good, is because they actually cared about energy consumption and designed it so it consumes less energy. Okay, so what do we do here? We have an ALU which computes stuff and the conditional block which checks for the condition. Are we gonna add conditional moves? By the way, this is the fact that they go through a component. This is insane. This is insanity. But I wanted to go different route. It's not gonna let. This. Okay, so whenever this is the jump mode. Whenever it's enabled. Wait, I just removed it. Last one. So whenever it's enabled, I'm gonna change the output to the first instruction thing. Oh, I mean to the to this third operand. There's this. Now where do I put the third operand? Where do I route the third operand? Here I can route it. It's not clean. Make it to go under, probably. So here it is considered an output, and here I'm gonna consider it an input. So this is a jump address in this case. In case this is enabled, and in case this is enabled, we also do jump mode. Okay, so I need also ideally I take a switch, but I need to put it like differently. So I stop jump condition if jump mode is not set. So like that. Now if so I can just connect, I guess, jump condition to jump condition and jump mode to jump mode, like that. And now this should still run. No, it doesn't. Add the immediate 0 argument 1. Oh wait, I forgot to connect the stuff. Forgot to connect a lot of stuff, you know, actually. Now this does work. Onwards. Functions. Unlocks something unknown, unlocks components, unlocks component. RAM unlocks component in the manual entry delay. Shift. So there are bit shifts, I guess. Hex racer. Oh my god. Okay, let's do hexadecimal first. And I'm not ending the stream just yet. Well, actually, I mean, I might soon. Second favorite pastime. Converting hexadecimal to binary under time pressure. I mean, yeah. Hexadecimal represents each combination of 4 bits in its own character. Yes, I know. Level 3 to pass. Okay, let's just do this. 1, 2. Okay, thankfully it does reset. 9. Wait, it's 9 plus 2. 1. Why is the first one always 0? I mean, I'm not complaining, but so it's like I feel like it didn't change in that. Remove 7 0 2 C. C says this. D. This 5 1 F. This is 1 and F is all enabled. 1 17 wait, yeah, 17 like that. 1 A B, another 1 B, wait, 0 D, E B C D. I mean, okay, I made it to level 3, that's the only thing that matters. Wait, they didn't give me a pass. Made it to level 3, they didn't give me a pass. Not playing that. It's not even connected to anything. Must be level 3 to pass. Oh wait, beat level 3. I haven't beaten level 3. Hey. 3 4. Look at my hand. 8 3 7 8 again. 1 C A B C 9 11 F 1. I am on level 3, 2, 3B, 3A, B, 1 AD. Wait, hold on. Okay, we reached level 4, that's the only thing that matters. It's a decimal. Total between signed and signed and hex numbers. Okay, now I can enable hex mode. That's interesting. So shift, RAM, and delay. I want to do delay first. So gate score and delay score. All components have a delay, and in circuit, the total delay is determined by the slowest path. This means you normally want to put things in parallel. In this level, we must prove that you understand this concept. Continue. So we derive from the delay of the basic gates, which have a delay of 2. Build a circuit with a delay of 6 and gate score of 5. Wait, what? Oh, so I only have NANDs, but I need 5 gates and 6 delays. 1, 2, 3, 4, 5 gates, and I need a delay of 6, so this is just need different colored wires. So I parallelize here. Oops. So I do parallel 2 lines. This one has 2 things. Wait, no. I need the longest. I guess, yeah, I need the longest. It's not gonna connect like that, so I do an end here. It's gonna work. It's just gonna work, so fine. Note, you can see the delay path by clicking the hourglass in the upper left corner. Delay. Manual entry on delay and configurable delay. For debugging and controlling the latency of the latency RAM. What? Latency RAM? Okay, show me the path. So 0 plus 2, this is 2. Plus 2, this is 4. Plus 2, this is 6. Okay. That is interesting. So we have RAM and shift. Yeah, I think we're gonna be finishing this later. Next time. So once we finish the functions chapter, push and pop, divide, product, enable, stack, the lab. That's gonna be fun. By the way, I haven't read the manual. So once we finish functions, we're gonna go and do achievements, some achievements. So I wanted to read the manual entry on delay. Hardware, all components have delay. This is important since the delay in the circuit determines the maximum speed at which you can run it. For wires from input to output, components path will give the delay of the path. The circuit delivers the slowest path. Besides inputs, path can also start from components with no round pin inputs, like counter and on. And they can end at also end square. Can end at also end at square pins. What? Further, custom components don't have delay score for the costliest path of the whole component, but rather the delay score is calculated per pin. This is so as to not penalize using custom components by making faster pins cost same as slower ones. Yeah, good. Okay, so yeah, we're gonna be finishing this stuff. We'll just look at how much we've done. Still kind of wanna fix some stuff here. Like conditional and ALU modules are just terrible, awful. By the way, since I now have the delay of components, can I gate score 79? Gate score of 79. So this is 0. This is 15. And each switch is an 8? You're kidding me. Each switch has a gate score of 8? That's insane. And the delay score of 2. Okay, I wanna optimize it by using ends instead. Then wait, I can't use it. I mean, 8 because this is, wait, 8 because this is an 8-bit thingy. So decoder is 15 gate score, okay. I mean, it's fine, I guess. And the multiplexer is gate score 17. Wait, why can't I see the hourglass here? And the gate score of the whole computer. 8-bit counter. Gate score 145, you're kidding me. I can't edit this, so it's fine. Registers gate score of 40, which is, well, this one is 0. This one is 40, delay score of 6. So registers are just fine. Gate score is 15, delay score is 6. Decoder. So I'm decoding this, and then I'm doing the decoding. I mean, actually, no, it's fine. I guess it's so good. Do I have 1-bit multiplexer? Of course not. I mean, why would I? I mean, that looks pretty good, except for conditional and ALU. I do want to redo them. Those two blocks. Anyway, we're gonna be doing it next time. So, oh my god. Camera latency is so bad. Camera latency was so bad. Okay. So we're gonna be ending here, and network error. Ah, I can't snooze it. I can't snooze that. Yeah, I guess we're gonna be raiding somebody. FLG UI learning FreeCAD. That's interesting. First I wanna check Turing Complete. Hi Jax. Yeah, you're a bit late. Yeah, did you get some sleep? Nigel, every time you see Jax and his stream, you rated pirate software. It's in 14 hours. Yeah, well, Nigel, if I'm not so if you are on Jax's stream and he's ending, just tell him to go to bed every time for me if I'm not gonna be there. Colonel. You did. That's good. Just in case. So yeah, I don't see anybody with stacks. I guess I'm just gonna raid this guy. Freak. I mean, I've been using FreeCAD for like 4 or 5 years at this point, and it was rough. But yeah. Before Ed starts, I just need to start the raid. And I guess I will see you later, next time, tomorrow, who knows. Thank you for joining, and yeah, bye.